Hello, everyone, and welcome to another episode of Simplified Network Automation with NetGuru. I'm your host, and today we have a special guest, Edward Bulharu. Edward, thank you so much for joining our live stream here. Welcome. How are you? How have you been?
I'm very excited. Thank you very much for having me. I'm very excited to attend your great show.
It's the pleasure is all on our side here on having you. Um, so tell us a bit about yourself. People might not know we've met actually. It was at Cisco Live Amsterdam this year, right? So serendipity made it that we got together. We were in Amsterdam for Cisco Live, both of us, and then we had a conversation. Back then, you were still looking for what to do in the future. In the meantime, I think you kind of figured out what you want to do. So tell us a bit about that. Where are you in your journey, and how did you get here, Eddie?
Yeah, thanks again for the invitation, Ede. So I'm an engineer at heart, and I started as a network engineer many years ago. I migrated to network architect positions, and during the last, I don't know, 10, 15 years, I was attracted by various AI flavors, and I started, I think, more than 10 years ago, building deep learning architectures to solve various complex networking problems. For example, congestion detection and performance issues within data centers, and that happened, I think, 8, 9 years ago. And I presented some of my work to various conferences and meetings here in Germany. I worked for major companies like AT&T, Kyndryl, Infosys, and I decided this year to become an entrepreneur and to build an AI native company in order to solve very complex problems.
Yeah, I mean, I'm impressed. We've talked briefly about this, but it's been a big jump. So super courageous. I wish you all the best in this new challenge. I know it's gonna be very tough, but at the same time, I'm sure you'll make it. You're super dedicated, and we're gonna talk about one of the applications today that you've built, right? Eddie, it's one of the applications you've built. Um, should we start looking at it? I think once might have got disconnected. Can you hear me, Eddie? I think we got disconnected here. Uh, Eddie, can you hear me? One, two. So while Eddie is joining, he has built basically an AI application, right? It's using 5 agents. We'll see in a bit architecture once he comes back. Yeah, Eddie's now. I don't see him anymore. But can you folks see me? You should be able to see me. Yeah, it works on my side. So I was saying the application that Eddie has built. Come back. Yes, I need that A2A and MCP info exactly. So hopefully he'll be back soon. But he had built an application with agents, AI agents, has split basically the functionality of network troubleshooting different issues throughout the network. So I hear you just fine. Okay, thanks, Plate Pursuits. So he had built this application, right? And it's ingesting syslog messages into one of the agents. that it does context routing based on what type of syslog message it is to another agent that after that goes and does, for example, OSPF troubleshooting, has a specific agent for OSPF troubleshooting, and that has been trained, that agent, to use an LLM that's been fine-tuned specifically for that use case, right? Or if it's a BGP neighbor adjacency, right, and goes to a BGP neighbor adjacency AI agent it's specifically tuned and trained for that use case. And oh, he's back. Hold on, let me see.
Yep. Can you hear again?
Yes, Eddie, you're back. We got disconnected there a bit.
Yeah.
So I was just explaining the application while you're joining back. So let's share screen and go and talk about the architecture. And I know you have some slides, so let's start sharing the slides and go over what your application does. Folks, this is the beauty of running these live streams. You never know what's gonna happen.
Yeah.
There you go.
Can you see my screen?
Yes.
Okay, cool. Okay, so I'm going to present probably the first integrated multi-agent network operation platform, which is using the latest state-of-the-art AI technologies, and which is intended to be a tool for network engineers and to enhance the network engineering teams. The agenda is split in 4 sections. First, I want to cover the fundamentals of AI agents. There are different definitions, different frameworks, and it's a good opportunity to use the same terminology, as well as I will cover the fundamentals for Google A2A and MCP from Anthropic. Then I will walk you through the application architecture, which is designed on 5 layers. Basically, I inspired from the internet philosophy, which is TCP IP based, which became so, let's say, so scalable. Then I will make a live demo to using an EVNG lab, which will be connected to this application, and then a theoretical level to see how we can build our own agent using Google ADK framework. The overall 5-layer architecture is composed of layer 1, which is the human layer. Here we don't have any agents. It's a dashboard which shows the status of various agents and incidents.
Can you zoom a bit, Eddie, please, if you don't mind?
Yeah.
The couple. Zoom.
Yeah.
Okay.
So this layer, this human layer, talks using ACP protocol, which is an IBM protocol, to the second layer, which is the strategic command plane. And within this layer, we have a team leader and a virtual architect. Each of them uses a fine-tuned large language model, which is specialized for their respective roles. Team leader acts as an orchestrator, incident delegator, let's say. Then this layer communicates with the execution layer, which is made of 3 agents. One for troubleshooting, which is basically layer 1, layer 2 troubleshooting. One for routing, which I called it stability agent, and one for security. The layer 2 talks A2A protocol with this execution layer. Every agent is powered by a dedicated fine-tuned large language model. I used for different agents, different large language models, which are actually optimized for that particular role. I will show a little bit later. And this layer, this agent layer, does not touch any device. This layer talks to a tool abstraction layer, which is the MCP layer. everybody I think knows that it's a very famous and standardized protocol now from Anthropic, which basically hosts a tool library. This is what it is. And this layer is basically communicating to a network infrastructure layer. In our case, we have a event topology with 3 routers and 1 switch. So an agent is an autonomous system which has multiple, let's say, functionalities. First, it must interact and perceive the environment. In our case, the environment is made of syslog messages. This is the environment, or this is how it interacts with the environment through syslog messages. Then, once the agent observed, let's say, an anomaly like incident, then it should sync a way to solve that particular problem. And here is where the large language model, which is fine-tuned large language model, comes in picture and helps, let's say, helps to identify the root cause and to propose a solution which should be implemented and it should be implemented within that environment. The thinking process of the large language model / agent is augmented by tools, because in order for a large language model to, or for an agent to make any hypothesis or to suggest any fix, it must first collect data from the environment. And here the tools are very useful or mandatory actually to gather all the necessary data for identifying the root cause and providing the right and the correct fix for that particular problem. So agents, together with large language models, they can interact in multiple ways. There are at least 2 philosophical models in which an agent can interact with a large language model. A common framework is when an agent communicates to a large language model its own set of tools. Every tool has a very clear definition. So the agent communicates to the large language model which tools has available, and the large language model understands based on, let's say, an additional query like we have on OSPF adjacency, plus with a particular set of tools, the large language model decides which tool should be used by the agent and returns a call function to the agent, and the framework of the agent, the runtime of the framework executes that particular function. So this is one way of interacting between agents and large language models, where large language model decide which tools should be used for a particular problem. One disadvantage of this, let's say, approach for our context, networking context, which is that is not very deterministic. And we all know that we expect that if we work with an AI, we expect an AI to have a deterministic behavior, which means that if we cannot rely on a large language model to decide which tools should an agent use for a particular problem. That's why we selected a different and more deterministic framework where the agent follows a workflow like an engineer, which goes through different phases of syncing, sequential phases of syncing. And the large language model, the interaction with the large language model is just for data processing and data analysis. Basically, a large language model, this is what a large language model does best: data analysis. So all this internal thinking happens within an agent, which is a deterministic workflow of actions. I mean, the tools and the sequence in which the tools are used. And the large language model receives the initial query, which in our case is a syslog or an issue, together with the output of the tools which were executed by the agents using MCP. So an agent alone is not very useful. That's why in order to solve complex problems, we need to develop complex solutions, which means to emulate how human teams work. And working in teams means cooperation. Cooperation in case of the agents is implemented using this Google A2A protocol, which has a lot of advantages compared to other ways of implementing this interaction or this communication between agents. For us, the most important architectural decisions were related to scalability. So A2A allows a scalable architecture, which means that we can plug in here multiple team leaders or multiple experts if we need for various technologies. And also very important is the clear boundaries. Clear boundaries is something which makes things clear and deterministic and allows also to scale out such an architecture.
Did you look at Cisco's agency over here, Eddie, as compared to A2A?
Yes, I did compare these multiple frameworks. A2A was one of the most in my understanding, and after all the tests I did, was a better fit.
Okay, all right.
I used here as a starting point Google ADK framework.
Mm-hmm.
I modified this framework to fit this particular networking, let's say, special requirements.
Mm-hmm.
So, for example, with one way in which I adapted, or I would say improved, Google ADK framework was, like I explained before, is that in order to have a deterministic system, a deterministic behavior, I don't want a large language model to decide which tools should use, which this is what Google ADK would do by default. And I tweak a little bit the framework I adapted to make it more deterministic, to make it deterministic. So an agent will execute a workflow for a given particular issue, and this workflow will provide, at the end of the day, will provide more confidence in the solution. So I don't, as I said, so I try to extract out of all the existing technologies available or which I tested the best of from each one.
Gotcha.
Yeah. Of course, for interacting for this interaction between agents and the environment, the standard solution is, the best solution by far is MCP. So how it is the best solution because it provides an abstraction layer for the tool libraries, which means that we can add or remove or change any tool within this layer without affecting any other layer, which makes it very handy. So the overall workflow, for example, in this example, when an agent wants to know what is the status of OSPF neighbors, so the agent initiates, let's say, this request through an MCP command. The right command is executed. A structured response, JSON response is comes back from the environment, from the network, and the large language model performs the analysis. So here, another reason why MCP is the best fit is large language models work way better with structured data. And if we would let's say rely on raw CLI output, I tested also with option. So even a fine-tuned large language model with Cisco documentation, troubleshooting guides, best practice, etc., a large language model performs not optimally, let's say, with raw CLI output. So that's why a tool or a mechanism like MCP, which allows us to provide to the large language model a structured data, is the best solution. So the overall architecture now in different format is consisting of is human, no agents here. It's a dashboard, an user interface. It's an approval gateway. This human control, human in the loop, this layer talks ACP to the strategic layer, layer 2, where is the team leader, which performs the task routing. It performs the task routing at scale, because here, if we need to scale this functionality, we just plug in additional team leaders and a load balancer in front of them. So we can use the same mechanism we use today for scaling the regular servers, adding a load balancer in front of them. And this layer, strategic command layer, talks A2A to the experts, to the agents, which again are powered. Each of the experts is powered by a different large language model, fine-tuned large language model, which then talks through MCP to the environment. We consider multiple design principles. Of course, as an architect, I've been, say, trained and very familiar with principles and design principles, and so that's why we apply the same logic to the architecture of this application. So to make a protocol separation, to have specialized large language models for various tasks, to abstract this tool layer, and most importantly, to have a human, which is the, let's say, provides the oversight of the entire behavior. So the team of agents is for stability. Stability here is for the layer 3 routing, basically. The font here is very small, but so for stability, I fine-tuned Quen 2.5 with 7 billion parameters. It's a very powerful model. For security, I fine-tuned Mistral 7 billion parameters. For troubleshooting, which by troubleshooting here I mean layer 1, layer 2 troubleshooting, I fine-tuned Code Llama. I will explain later why I selected these models. And for the virtual architect, because it's the architect, I picked up Llama-3 with 8 billion parameters from Meta.
Okay, so I mean, these LLMs are not super large, right? So they're, small to medium, I would say. And tell us a bit about just a couple of sentences about the fine-tuning of these LLMs, Eddie, because we probably going to have a session specially dedicated to that. But how do you fine-tune these models, right, for your specific use case? In this case, security, troubleshooting, and what you had like routing for OSPF and BGP. Like how do you do that?
Yeah. So first we start with defining the task we want to solve. So let's say we want to fine-tune a troubleshooting large language model, which should be expert in troubleshooting.
Networking, right?
Networking troubleshooting. Okay, so that means that we should. There are millions of large language models on Hugging Face. There are, I don't know how many vendors which are periodically make open source large language models. So the thinking criteria here, the blueprint, if you want, is to see, okay, we need to understand how that particular base model, how it's called, how it was pre-trained. So some models like, let's say, OpenAI, which is very popular, was pre-trained with the entire, or big chunk of internet. So it's a generalist type of AI. Other models, like for example, as I said, for troubleshooting, Code Llama was pre-trained. So in the pre-training phase, was pre-trained uh, with a lot of code, which was used by the developers to, which means that this Code Llama base model already have a very well understanding of what is the logic embedded within within various programming languages, within various syntaxes, within the. So it's a very good programmer. He has a very good understanding of what are the fundamentals of programming, because it was pre-trained with, in this case, almost 500 billion tokens on code. Token is almost three. It's 0.75% of the word, roughly speaking. So we can approximate a token with a word. So it's an immense amount of code used to create a base model like Code Llama. So then I took this model because this model already knows programming. So then the effort to create a data set for specific Cisco syntax was relatively easy to create such, let's say, data set for Cisco or for any other vendor for that matter. And okay, so and then the next question is, okay, how big should be the model? As you know, all the vendors release such base models in various sizes. So here comes somebody. Here is a commercial. It's a commercial question, because in order to deploy and to deploy and to fine tune such model, we need a relatively high amount of GPU, which is pretty expensive. So we need to also to factor in the economics of the what is our available budget to how much GPU can we afford, how big that GPU cluster could be for our, let's say, for our project. So once we know which is let's say, because this is a standard design constraint. Yeah, cost is a constraint. It's a design constraint in any industry, in networking, in any industry. Cost is a constraint which should be factored in during these early stages. Okay, so based on the size of the available GPU we can afford for that particular project, we can pick up several base model candidates. And we start this process of fine-tuning. This process of fine-tuning requires first to create, let's say, to identify which are the best hyperparameters which are required in order to create the in order to in order for the model to learn the underlying patterns of our data, in this case Cisco troubleshooting commands. So in order for the what you want to achieve at the end of the day is that the model should be able to, from the learned data, should be able to generalize on unseen use cases, and to be able to say what is the, let's say, the a SIP or a command for a given problem based on the huge or relatively huge amount of data within the data set. So we have a base model, we have the data set, and we have the GPUs, yeah, the hardware. So we need to find a mix between these three dimensions, and there are no magic answers. It's mostly is a trial and error. It's you just need to play with various hyperparameters to see which let's say instance of your fine-tune model performs the best.
Yeah,
So this would be, let's say, the overflow.
Yeah, critically important is also the data that you feed in, right? Like you said.
Absolutely.
So that would be probably the most important thing. And this is basically for Cisco would be cisco.com documentation, all the commands that are there, right? For configuring SPF, all the routing protocols for troubleshooting. It's basically that's the type of data that you feed in those documents, right?
Exactly. Not the documents per se, but the data should be the data within the documents, which should be formatted in a certain way. Which the way in which data should be formatted depends on the specific vendor. So this information or this the structure of the data is public available, so it's easy to find and to see how data should be formatted, what should be the structure of data. But as I say, yes, the quality of the data is by far the most important, parameter within this, let's say, multi-factor equation.
Gotcha. All right, so you decided, right? You've looked around at the millions of LLMs that they have on Hugging Face, and it's like, okay, I'm gonna go with Mistral for team leader and security agent. I'm gonna go with Quen for stability agent, and then troubleshooting. You said Code Llama, and then virtual architect is Llama-3. How did you get to these specific models?
Okay. I don't want to go into the specifics of the transformer architectures for each model, but here, what would be, let's say, a fast answer to your question is that, let's say, Mistral. It's a model which uses specific query attention mechanism, which is called grouped query attention, which makes possible a better classification from the pre-training phase. So I'm very interested in the strengths of a base model, which resulted which are the result of the pre-training phase. So a model like Mistral, it's not the only one, but yeah, a model like Mistral performs very well in pattern matching and classification, and it's a best candidate to act as a dispatcher for incidents. Troubleshooting with Code Llama is, I mentioned earlier, Code Llama already knows code, so it's a quick win. Stability. This stability, it's a routing. This is layered. It's a routing agent. Let's say. I use this example Quen because Quen is a reasoning model. It uses a different architecture, and his internal mechanics is more suitable for complex problems like routing. When let's say we have let's say we have a BGP peering issue, and it's an entire syncing workflow an engineer should go through in order to go to the root cause. And it's not like in case of I don't know, in case of troubleshooting, just searching for the best commands to implement a solution, but it requires a different, let's say, paradigm in terms of how the problem is processed in the first place. It's not a simple next token generation model, but it is, in case of stability, where it's a reasoning model which goes through steps like chain of thought, starts with the problem, then goes to the second step and the third step. So this was the logic I used when I picked up these models.
Gotcha.
Yeah. And for the virtual architect, I selected Code Llama. Well, this is something which I did, I don't know, 1.5 years ago. So it was one of my first projects. So yeah. So why 8B for Llama versus 7B? Because I saw that a virtual architect should manage, let's say, a little bit more complicated problems, and that's why it might need an additional bidon parameters, which is roughly 40% more capacity to be able to solve design networking problems. And also has a little bit, the context window is a little bit bigger. The context window basically for a model is equivalent to RAM memory. So it's something which can be used during the session. Yeah.
Okay.
Yeah. So this is the virtual architect. Yeah, I mentioned I used various as a original data, various design guides, best practices, topologies, different things to help the model to understand the underlying logic within, let's say, the networking design, because there are some principles, there are some mechanisms, there are some rules and architecture, let's say, way of thinking when we do a design. So this stuff is all these things are embedded within data. So the reason, as I said, I use eight bidon parameter was just because to have more, let's say, more parameters available for fine tuning.
Mm-hmm.
Yeah, I think we already covered with fine tune in the previous
Mm-hmm.
discussion. Also, all the models, all the agents, all the agents have fallback. Fallback can be any model. I've used OpenAI GPT-4o Mini just for convenience,
Mm-hmm.
but every agent can use also multiple large language models, and yeah, is the advantage and why it matters. I tested several. I don't know. Last year I tested OpenAI versus fine-tuned large language model, and I've seen and I documented at that moment that a fine-tuned smaller language performs better than a generalist model like GPT-4. The speed is also it's a little bit better compared to commercial models, which are again generalist. The cost is theoretically zero. The only cost is the hosting or host, but we don't need to pay for inference as long as we have these models available on-prem. And probably one of the most important reason is privacy. Privacy means that we don't need internet connection to run such an AI solution. Everything is local. The overall workflow presented in this diagram. So everything starts from layer 1, from router.
Mm-hmm.
Layer 5 router, which sends syslog to team leader, which is on second layer. The team leader performs this classification because he was fine-tuned on a lot of thousands of incidents and understands the nature of the incident. Let's say routing protocol in this example, on this slide. And the team leader performs using the A2A protocol, performs a delegation, which means that it sends a message to the stability agent invoke. Stability, as I said, is the routing agent, basically. And the agent makes a pull request to MCP to a given set of tools, which are which equip basically this agent. The agent then queries the data, takes the data from the network, then the data is returned as a JSON to the agent, and agent hands over the data to Quinn, to this fine-tuned large language model, which will propose a solution. And the solution will be handed over also through A2A to the team leader. And the team leader will send this using an approval queue, will send using ACP, sends to the user interface for review.
Mm-hmm.
The principles and the decisions, we need to take several architecture decisions are presented here in this slide. Probably the number one architectural decision, which is also an ethical decision, is that human must be in the loop, and this solution should empower networking engineers. So this is our ethical principle we applied within this architecture decision. Another important principle we used is this layer separation, to have specialized agents for clear tasks. Another principle, which is one of the strengths of this application, is that it uses fine-tune experts, which gives all these, let's say, advantages I mentioned earlier. And last but not least, MCP. So in a real scenario, we have a traditional approach where an OSPF issue is solved probably in, let's say, 1 hour. Within an AI Dream Team approach, how we call it, once a syslog is received, a team leader needs 4 seconds to classify it with Mistral. Then the stability agent will analyze it, and it needs another 4 seconds. Then MCP will fetch the data from the network to make possible this analysis of Quinn. And in second 15, the human is able to approve the fix coming from the agent, which is 300 times faster than
300 times faster. That's unbelievable. All right,
yeah.
all right. So we got a syslog, right, generated. Then we have all the so OSPF neighbor down. It goes through all the steps. Basically, from the syslog goes to the team leader. From the team leader goes to your agent, right? The agent goes through MCP to the infrastructure, gets the information of that actual what the actual issue is, right? It was like, oh, OSPF is actually down. Yeah, stripe your OSPF neighbor, and then suggests a fix, right, based on the LLM, right?
Perfect. Yeah, perfect. You perfectly understood. Yeah. So, yeah, this is what you described.
Okay.
Yeah.
There you go.
So we use all this standardized protocol, which means that if we want, for example, to swap any layer, we can swap it, and we can use we can use any, let's say, any variant for every layer we want. That is the beauty of standardized protocols, because each layer talks, like in TCP, talks to only to adjacent layers via standardized protocol. So if you want, for example, to swap the user interface is implemented now with Streamlit. If we want to swap Streamlit with Slack, for example, or any other front end, we just need to change a container from this architecture, and we have a different user interface, and we don't need to touch any other layer of the application. In terms of security and safety, this idempotency, it was an issue we faced, and we fixed it using Redis cache. It took us a while to do that. We had this issue with same command, which was executed multiple times, because every time when OSPF or JCC goes down, the OSPF router will generate multiple logs, and for every log, the agent generated the same command, and we fixed it using Redis. Then, of course, human in the loop, which is super important because every decision is logged with a timestamp, and open fail design here implemented with circuit breaker, which means that if somebody tries a denial of service, or then the token budget will limit and the application will stop working. The technology stack used here is described here. So from the infrastructure point of view, Docker, my network lab is in Azure, is EVNG, which I will show you in a minute. For parsing, I use text FSM, and observability is not yet ready. It's on roadmap. We're still working on that. The core technology is important because all the 5 large language models are deployed on endpoints on Hugging Face. So for each large language model is deployed on its own endpoint on a dedicated instance on various cloud providers, GCP and AWS. What else? Yeah, for messaging,
Redis, yes.
Redis, and Streamlit and Scraply for automation. I think the return on investment for such approach is obvious. The detection is, the overall process takes around 15-20 seconds, which makes the cost 1 cent per incident. The performance gains are simply not possible to compare with humans. Simply the scale and speed is unbelievable. And again, in our approach, I think such tools should augment networking engineers team. So, in terms of technical innovations, we did is this mix of ACP, A2A, and MCP, augmented by or powered by fine-tuned large language model specialized and integration with real integration with an environment like Cisco and EVNG. The roadmap is what to expand it to also analyze BGP protocol. The security CV is almost done. Our team already finalized the security CV automation solution, and digital twin is also implemented and should be digital twin to be used to validate in a digital network, which is it's a one-to-one representation of the real network to test whatever the agent recommends. And if the result of the change is not correct or does not fit to the baseline, then the agent will reiterate and start thinking to fix it. So all the error and trial and error approach will be implemented within a digital twin instead on production. So the challenges. So what worked well, I think, is not interesting. I think what is interesting is the challenges. So challenges we had with noise, token noise from Llama, duplicate approvals. This is still something we struggle and try to fix it. And in terms of best practices, I would suggest to start with a simple agent with OpenAI. It's very accessible, and then to add fine tuning later, and then to log everything and test with synthetic data. We don't need necessarily an access to a lab or a real environment, and to document everything, to document because things are so dynamic and a lot of things, or in my experience, I did at the beginning, I did a lot of mistakes, and well, the biggest mistake was that I didn't document them. But once I started to document them, we started to reduce the number of them. So yeah, so let me walk you through the so visit the lab. Let's take a look on
Mhm.
visit the lab. So let me make sure that everything is running. Just to make a baseline.
All right. Yeah, interfaces are up. What about OSPF neighborships?
Yeah, we have one neighbor. Okay, so that
Okay.
means one. Let's see who is. Okay, so the
Okay, so this is
interface.
a test network.
One more here. Here I have the interface now. Let me check.
So this would be your test network, right?
Yeah,
Eddie,
yeah.
is in event G, you have a small topology of a handful of devices here. And you have OSPF running between these routers, and they're established the neighborships. Oh, you have an interface down over there. That's why that neighbor is down, right?
Yeah.
Gig 00, no shutdown. That will be INT. Yep, no shut. That will bring up the neighborship,
Yeah.
or bring the interface, and then the OSPF neighborship will come up. And then you want to simulate basically that interface being down, right? And that's going to trigger the syslog message. It's going to get picked up by the
Yeah.
team leader. That's going
Yeah.
to trigger
So
the more workflow. Yeah.
exactly. So if we look at the application, the front end, so we have these five endpoints, which well, these are the large language models which are up and running in Hugging Face. Here we have an AI chat, which we can talk to the virtual with the network architect, and let's test it. What is best OSPF design? Let's see what if it's available. If it's not already on
It's a
vacation.
loaded question.
It takes now 10-20 seconds.
So, I mean, these models, you could actually also run them on a beefier server, right? Because they're like 7, 8 billion parameters, and it's 5 of them. Because I've been running with Llama on my work Mac, right? I can easily run like a Llama-3 8 billion parameters without a problem. So if you have, and by the way, how much GPU would you say would you need to run all these 5 LLMs on a server, on on-prem server?
So for the math is relatively simple. So for every billion parameters, we need to multiply with 4. So
Mhm.
if we have sorry, I couldn't. I need to check the yeah. It's let me check here because so for 8 billion parameters we need
32 gigs of RAM.
32
Yeah.
just to download it in GPU, and then to perform inference, which means what I try to do, but the endpoint here seems that has an issue. For inference, another couple of gigs, which means that in order to safely run 8 billion parameters, you need around 40 gigs GPU, which is available in Colab for yeah. Okay. Meanwhile, let's test the troubleshooting agent to see if it works. So let's shut an access port because this is a troubleshooting agent. Let's see if it's working.
Okay, so shut down the interface. Did you have OSPF running on there too on that?
It's an access port. And here we need to wait. This is the approval window for the agents. We need to see here in a couple of seconds. We need to see the outcome from the troubleshooting agent, and we have it. So the troubleshooting agent, and here we have a timestamp which is 14:57. So it was now basically it's a GMT time. So this agent picked up the interface which was down, made the root cause analysis. Of course, we gathered the evidence, and we see here the AI model which was triggered. The AI model which was used by, unfortunately, we need to update this to a bigger font. The AI model which was used for troubleshooting was called Llama-3-8B, and proposed fixed. So this is the troubleshooting agent in action. And if we do the same to trigger, let's say to trigger the
OSPF interface, right?
The OSPF interface, we should have the stability agent, how I call it stability. Maybe I should name it to a different. If we so this interface runs OSPF 00. So if we shut down, we should lose the OSPF adjacency. So yeah, so now this is what we see with deduplication. It took us a while to deduplicate these messages because every message triggered a command. So if you look now on the app, in a couple of seconds, we should see the stability agent, which should say something.
And then you have also a button there, right, for approve. This is the
I have a
concept that you were talking about. So you can just approve there, and that will go and basically run those proposed fix commands.
Yeah, exactly. So here the operator, the human in the loop, has the ability to approve the code. I have the code, but it's not wired up. So the idea to approve is just to push this no shut command into on the router, or it has the ability to reject this proposed. Yeah. So meanwhile, we see the stability agent which kicked in. We see here is another model, is Quen7B, that reasoning model which I mentioned earlier. Identify the OSPF neighbor transition from full to down. Evidence, collected the evidence with MCP, and the solution to of course, to no shut the interface. In this way, also you can compute risk for the and the confidence level for the change. That's why, in order to be 100% sure, let's say a digital twin might be a good say improvement to such platform to test whatever is proposed here in the
Mm-hmm.
digital twin to increase the confidence to 100%.
Mm-hmm.
We see the time analysis time, which was 7.9 seconds, and consumed 1,200 almost tokens on Quen 7B. So
Very nice.
yeah,
Okay, so you have basically a self-detecting, almost self-healing human in the loop, right? Because it detects based on syslog messages, whatever happens in the network, all your agents are monitoring those syslog messages as they come in. And the nice thing is that it gets context routed to whatever agent is going to be able to address that issue. So like you've shown, right, the access interface went to the troubleshooting agent, the OSPF neighborship went to the stability agent. So it gets redirected and routed to whatever agent needs to go to for that issue to be fixed, or a fix to be suggested to the human. And then the human, if wants to approve the fix, goes and presses the button, and that automatically connects to the device in the backend and applies the commands that were suggested. Right?
exactly.
That's pretty much it, Eddie, right?
Yeah, exactly.
Okay.
Exactly.
Well, yeah, I mean, this is fantastic. So, what's the plan then with this? Are you gonna open source this product? Are you gonna start selling it? What do you have in mind?
Oh, we thought about that, and I think we will open source the core of this application, which means all these agents interactions and all the guidelines to develop as many agents you want using these protocols and using this user interface. And for commercial or for enterprise features, all these fine-tuned models most likely will stay a while under our management. But the backbone of the application will be open source. Yeah.
Okay. So once we have that, we'd love to put that repo, hopefully a public repo, in the description of this video so that folks can actually go and
Yeah.
see and basically replicate and build their own agents. You have here 5 of them, but I mean, there's no reason not to have more or to scale this. Like you've said, you can easily put a load balancer in front of the stability agent or the troubleshooting agent, and
Or
you can
team leader.
scale that to, getting hundreds of thousands of syslog messages per second if that's the environment that you have. All right, very, very cool. Some final words. We're a bit over time here. Final words, Eddie. Thank you so much for showing us this and your solution. This is very nice.
Yeah. Thank you very much also for the invitation.
Thank
Yeah.
you.
Any
Thank you for
questions?
coming. Yes, please. For the final message from you.
So I encourage everybody to slowly start playing with AI. I would recommend to start from fundamentals, which is what is a deep learning, how can we build a deep learning, then to go easily to understand at a high level a transformer architecture, and to move easily to prompting, to RAG, and then to fine tuning. And if this learning cycle or learning curve is done, which probably it's a function of I don't know, couple of months probably, then all these things will start to make sense, and AI will become a real tool and real support which should augment our daily activities. That's why AI is created in the first place, to help humans to be more productive and to produce more value for us and for our companies and for society.
That's the perfect message to end this, folks. Get on it. It's not that complicated, right? Like Eddie was saying, start with the fundamentals, look into what these LLMs are, how they're working. You don't need to go into all the super deep math, though, right? Because there's a lot of advanced mathematics going on behind it. But just to know a neural network, what it is, how it works, right? What's your input data, output, how you train a model, how you fine tune it. These are all very useful for you to understand what's capable. And once you know what this technology is capable of, then you can start applying it to your own use cases, right? Like network troubleshooting or configuration or ticket creation or closing tickets or escalating or whatever the workflow or the use case may be for you. Thank you all for watching this. Hope you folks found it useful. Eddie, thanks again for coming on live stream. Was super insightful. And look back at for you to come back and share some more information with us once you make a bit more progress with your application. And for the rest of the folks, we'll see you next week, folks. We'll bring back David Flores and Christopher Adele next week. We'll wrap up their network observability book. It's going to be episode 3. And we'll wrap up. We've already had 2 of them. And so excited to have David and Christian back. And that's it. See you folks on the next one. Take care, everyone. Thanks, Eddie.
Thank you, everybody. Thank you very much.